Welcome to this unit 17 and 18, just before the second midterm. I try to keep the actual lecture as much review as possible, also with the examples. Here a quick overview over the setup for triple integrals, and then we are also integrating in spherical coordinates or cylindrical coordinates. So the setup for triple integral is theoretically the same than what we have done in one dimension or two dimensions. What we integrate over is a solid. Now we have a three-dimensional object that's much richer. Solids can be much more interesting than regions, and we are integrating over that. And in order to integrate over that, maybe that picture is a good picture. What we do is we split up the region into the solid into small little pieces, and we take the function value at the piece and we add that up and multiply with 1 over n cubed, which is the small volume element, 1 over n cubed. But this is not how we are computing triple integrals. That's a computer can do that numerically. What we are doing is we reduce it to either a single integral or a double integral. I always call this burgers or fries method. So we mostly will just do the fries method. The burgers method is a method which you are familiar with single variable calculus. You reduce things directly to a one-dimensional integral, and then you can use single variable calculus. So let me just illustrate this with something forbidden. Don't tell my wife that I'm actually eating here some burger. Maybe a year that I have not eaten anything like that, and it's forbidden in our home. But what we see is when we have the burger method, we have all these slices. There's bacon, there is beef, there is lettuce, there is tomato. And what we are doing is we take the function which we have and then we integrate over the lattice. For example, this could be the area of that piece. And then we add up all these pieces here, which is a single integral. The burger method. And then there is the fries method. That's what we actually will do most of the time. So if you have the region, what we have is the region is made of slices of fries. And so what we do is we integrate over a two-dimensional region, and then we have a one-dimensional integral inside, which we then evaluate first. And then what we have is just a function. We have a function of two variables. And then we are in business like what we have done last week. We have a double integral. But in order to illustrate this burgers and fries method, let me just show you something you know how to compute the volume of a cone. So this is a cone. We put it upside down, and I just assume here that the radius is just z. So at height z, the r is equal to z. And we want to compute the volume of that cone. So if you are in single variable calculus, you just look what is the area of this thing. So you integrate here from 0 to 1, dz, and then what you integrate is the area. You take the area, and in this case it's pi r square. So pi r square, and r is equal to z. So we have z square. This is an integral we know how to do, right? This is z cubed third. So this is just pi third. This is the other method here. What we do is we integrate over the base. So what we are doing, like before, this is a bottom to top integral. We start at the bottom and we integrate up. So the bottom part is square root of x squared plus y squared. And the top part is the roof here, that's equal to 1. So it's very important, and I should have mentioned this earlier, that when we take a function f, which is constant 1, then we compute the volume. So if I want to compute the volume of this melon, I integrate the function 1 over this melon. And in general, you think about this f as a density. Like in this case, maybe it is more dense inside because there are some seeds, and maybe also at the outside where the shell is, it's maybe more dense. So you can model this, and if this is a mass density, then you get the mass. This integral here would be a hypervolume. It would be in four-dimensional space. Think about this as density. Could be also charge density, and then you'd have the total charge. Could be population density or a density of a chemical agent, and you compute the total amount of that chemical. So let's just do this integral. That's a little bit of review also. So we integrate over r over this circle here, 1 minus square root of x squared plus y squared, and then you have dx dy. And now we are in review mode. We have a double integral. We are no more dealing with triple integrals. And you go into polar coordinates, then you use theta and r, and then from 0 to r, and then we have 1 minus r. And then don't forget the integration factor. So the volume of that cone is just the base area pi times the height over 3. The last thing I want to tell you here is about the setup of the integral. That's one of the hardest things in this triple integral thing, and it's always the good advice is think 2D. And then you integrate over r. What do you integrate? You integrate from the bottom to the top. Maybe that's just the surface, yeah, z is equal to 2 minus x minus y. So you actually integrate over r 2 minus x minus y dA. Also here, that's the famous hoof problem of Archimedes, which I have here just built with Play-Doh. So what it is, it's a cylinder which you have just cut so that there is a half circle on the bottom. And you integrate over r the function which goes from 0 to x. Get immediately to a double integral. Once you get to a double integral, you have no more to think about space. And finally, this unit 18 is something which is very useful when you integrate in space. And actually all these peppers here, they can be described pretty well with spherical coordinates. You just have the radius depends on phi and theta. And the only thing which you have to know is that when you go into cylindrical coordinates, which means polar coordinates in the xy plane, that you have to introduce that factor r. In the case when we do spherical integration, you get the factor rho square sine phi. I have made you here the pictures, showed you the pictures which derive this. So what you have is a spherical wedge here. Let me just show you that. I always like to show that with a actual melon. I don't have a good knife here, so I've only a scissor here. But if I'm cutting here, a beautiful spherical wedge. So maybe I cut away a little bit here, and so small part of the radius. Now I have a spherical wedge. So this is this part here. So what we have is d rho, which is the radius change, and then we have rho d phi, which you see here very well. So that's this length here, rho d phi. But then there is also this length here, which depends on r, not rho. But r is equal to rho sine phi. One of the great applications of this is that you can easily compute the volume of a sphere, for example. Not like Archimedes. Archimedes did it in a clever way by just relating the volume of a half sphere with a complement of a cone. We don't want to compute only volume. We also want to compute things where we have a function which we integrate. And one of the great applications of this is to physics, where we have we integrate x squared plus y squared, which is the square of the distance to the z-axis, or the axis of rotation. Now, the moment of inertia is not much more difficult. What actually happens is you just have to, when you compute the moment of inertia, this is r squared, which is rho square sine square phi. And we will see how to do that using a double angle formula. And that's it for today.